Without further ado, I'm delighted to welcome Austin Gilliam to this very special installment of Circuit Sessions. Austin is a software engineer working at JP Chase. He graduated from the Ohio State University with a master's in computer science and engineering, where he specialized in machine learning and robotics. And while working towards his degree, he also contributed to projects providing software products and solutions at JP Chase over the summers, and then joined the bank, the advanced computing team, after he graduated. Has been working there developing software solutions for complex financial technology problems. He continues to focus on machine learning, but now he has added cloud computing and quantum computing to his repertoire. So Austin, welcome, bienvenido, and thank you for joining us today and sharing with us a bit about you and your experience with quantum computing, your perspectives on quantum circuits. And thank you for agreeing to tell us about your research. It's a great pleasure to talk to you today.
Yeah.
And I bet more than one of the people tuning in would like to learn how you ended up working in quantum for finance. So why don't you start telling us a bit about Austin and your journey to quantum, and maybe like offer some advice based on your experience to anyone wondering how they get started in quantum.
Yeah, sure. So I would say the journey for me has largely been about the people. So like you said, I joined JP Chase full-time in the summer of 2018, which was about 6 months into the academic partnership that we have with JP Chase and IBM for quantum computing. I work in advanced computing with Konstantin Gonchula, who is one of the distinguished engineers at JP Chase. He's been the co-author on all of my papers thus far. And he really got me started. I would say he challenged me to think differently than a developer, which is the way that I've been functioning in the past, and think more like a researcher. And I would say the rest of the journey really falls apart without that first step. It's pretty crucial. But then we've been collaborating with IBM since I started, right? So that's kind of how I got into this field. And so, for example, the work that we did with Stefan Warner last December, which I'm sure we'll talk about, and he taught me a lot about quantum optimization and circuit optimization in general. So it's kind of like that next step, coming from basics to maybe a little bit more niche. Special shout out to Joel Chudo, by the way. Wanted to make sure I put that in. He pretty much helped me with every question that I had. If he didn't know the answer, he knew someone who did. I would be much slower without him. So props to that guy. And then, yeah, I would say that sort of progressed for the past 2 years or so that I've been involved in this effort. And then really the last piece in the puzzle that I needed was sort of the cadence. So in January, JP Chase hired Marco Pistoia from IBM to lead Flare. So you may have heard of that headline. And Flare coordinates all the quantum computing research efforts at JP Chase. So with Marco's support, we've got a lot more consistency in our efforts, and I expect that we're going to see that as we continue forward with quantum computing. So that's sort of like where I am now. So I'm in this sweet spot where I have all the support I need. I have that basic level of training, so that most people I think would have when they're starting like a degree in this field, for example. And now we're diving deeper into what actually makes these quantum algorithms work, what's important, and I think more importantly, what we can change. As far as getting started for other people, right? I'm aware that I'm a special use case in which I kind of got thrust into this and was paid to do it. But I will say, from a computer scientist perspective, I'd never done anything with quantum computing before, not in college, not even as a hobby. I knew what it was, but it was really starting from scratch. And I would say you don't need linear algebra to get started. And there's going to be some mathematicians that get very angry at me for saying that. I would say understand the quantum state first. Like, really, what is the quantum state? What does it mean to work with a quantum state? The quantum computing postulates, I think, are a good starting place there. If anything, if you wanted to get into the mathematics, it's more important to understand binary strings, in my opinion. So like combinatorics and things like that. To actually like think about how the computing in quantum computing works. And then, of course, this is coming from the computer scientist, but write code. So even if you can only commit to like some private repository or internal company repository, do that, or contribute to Qiskit. It's open source, so we've had a couple contributions that we have either submitted or are working on, and even that process, right, getting feedback from the people who know what they're doing about and they're really ingrained in this stuff has been really nice for my education.
I know that's very good advice. Thank you. So, guys, don't be intimidated. Jump in. There are great education resources out there. Start writing code and just learn by doing. So, what can you tell us about your research interests?
Yeah. Okay. So in general, I think like everyone, we're looking for what business problems can benefit from quantum computing. I think everybody wants to know that answer, but no one knows for sure what that looks like. Anyone who tells you for sure, I would be a little bit concerned. And so we have groups in the firm that have released papers on things like portfolio optimization and option pricing, and you can go look those up there on our archive. However, we're learning that it's more important to learn and design patterns. And when I say patterns, I mean sort of like design patterns from back like software in the 90s. And that's simply because, like they found back then, they can be applied to many business problems, right? So you kind of go that level deeper and you get a lot more functionality. So we've sort of set some tenets, right? Like everything has to be runnable. We don't like to keep things purely theoretical. We really want to simplify all the noise that's going on in this space right now. And we found that implementation really leads to the understanding. And because of that, right, we stress a deep understanding of the fundamentals. So if you don't understand how, say, the quantum Fourier transform works or how amplitude amplification works down to like the amplitude level, like what's happening there, really the spirit of those algorithms, right? What the authors were intending to do when they wrote those papers, and not necessarily the letter. And I would say, in general, this is really paid off for us. That's why the papers that I have put out and some of the ones that we've got in the pipeline for the future really focus on this. And then we're finding more and more that once we find that small piece, people will come to us and say, hey, do you know that this solves this business problem? So yeah, that's where my interest lies.
No, I mean, I love something that you said, implementation leads to understanding. And that's
For sure.
so true, and it's so important, particularly when we're doing research to understand what's really possible in practice versus theory.
Yeah.
So let's talk about quantum circuits, and I have a three-part question for you. So
Okay.
What is your perspective on circuits as a computer science major? How do you see the difference or challenges of quantum circuits versus classical circuits? And is there a particular class of circuits that is more useful to you for the problems that you care about?
Okay, so yeah, I would say as a computer scientist, again, I don't think this is surprising. A circuit is the closest thing that I get to code, and in this field. And I would say, in general, I'm a big advocate for making code available alongside papers. So typically people do this by putting like pseudocode in their paper themselves or attaching a GitHub where you can, right? I realize there's some proprietary things like that that will stop. But if you can do it, I think it should be there. And quantum computing is great in that, like, you just put the circuit on the page. So that's really great. I love looking at how something is implemented, particularly because quite often there's a theoretical idea in quantum computing that has multiple different implementations. So sometimes I'll read papers on the same topic just to see, what differences there are. And I would say sort of how important circuits are to me then from that perspective is that I rarely engage with a paper that doesn't share the circuits that they're running. I really, even if the circuit is theoretical, right? Like it says, like if you have some unitary that does this and you apply it in this way with these controls, that is much more valuable to me than just math. Second question was challenges.
Yeah, like how do you see the differences or challenges on working with quantum circuits versus classical circuits?
Yeah, so I would say, kind of like tying in that question on getting started, it's really sufficient just to run a circuit. There's a lot of information. It's kind of like music. My fiance says that all the time. She'll look at it and say they look like music notes. And in the same way that you can look at a book full of music notes, right? And just say, oh, okay, that's nice, and you can kind of guess like this is going to be loud and this is going to be quiet. There's a lot of information baked into that people try to understand all at once. And I would say just run the circuit, right? And that'll get you somewhere. More importantly, try to understand what each gate does. A lot of people, I'm not like ragging on linear algebra or anything, but people will love to just give me like the matrix and say, hey, here you go, this is what this gate does. Which, in a way, there are probably people that go, great, absolutely. But for me, I'm like, okay, but what does it do? Like, what is the spirit of this gate's purpose? What's it about? And then from there, I think, especially if you have an engineering background, once you have your components, you can follow your engineering intuition as to how those gates can work together. And then, start worrying about depth, complexity analysis for your algorithm. Eventually, if you're like me, you'll find yourself starting to look at how pulses work and getting down to that low level. So really, as far as challenges go, is don't get bogged down in the information. Allow for a natural evolution of your education of what's going on there. Really don't force it.
Yeah. So I see there's a question about do you have to work with pulse level programming? So I think this is a great point to transition and see if you can show us then an example of how you use circuits to build applications and solve useful problems in finance, and then maybe that can address also the question about pulse level programming.
Yeah, so I can say just first, the stuff that I want to show is sort of from the past December. I would say my interest in pulses is relatively new. So do I have to? We're getting there. I'm getting to a point where I realize that, I could, if I want to be the most efficient possible, I kind of have to go to that lower level in the same way that, like, if I'm coding in Java or C, right, I could probably make a more efficient program by dropping down to assembly. But then you have to understand all the nuances of whatever assembly language that you're in, what hardware you're on, so on and so forth. And so it's that same natural desire to go that level lower. But yeah, I can share my screen here. There we go. See my screen all right?
Yes, we see your screen.
Perfect. So yeah, so what I just as an example of the kind of stuff that I work on. So last December, Konstantin and I released a paper with Stefan Warner from IBM, and we've committed the code from this paper in Qiskit Aqua, and this notebook is actually in Qiskit tutorials. So if you want to go look at this after the stream, feel free. It's available right here. And the idea of what we're doing here goes back to those fundamentals, right? So we were looking at how do I encode a problem? How do I, search for the solution to that problem, so on and so forth, and really going down into what kind of components quantum computing could offer us. So the idea for this particular work stems from this idea in classical computing where I have an optimization problem and I want to see if I can turn it into a search problem. And so if you're familiar at all with machine learning, this might sound like a no-brainer to you. But we were, again, still sifting through quantum computing, and I think it was Stefan that came up with the idea to ask, okay, if this is what you want to do, maybe try Grover Adaptive Search. And so the goal here is to find the optimum of a general function. And in this case, we're going to use the minimum, right? So let's just say I have some polynomial, right? And it is going to have monomials that will have coefficients, and I want to find the minimum of that polynomial. To get started there, I really need to know three things, I would say. How to efficiently encode that search space, which you can do with anything similar to what I'm going to call a quantum dictionary, which is something that we described in one of our earlier papers. And the search space is just the values of that polynomial, right, in superposition in the quantum state. And if you're not familiar with how this would work, it's just that the output value is going to be the sum of the monomial coefficients, and the digits in the input are going to determine which monomial coefficients contribute to the output value. So I have two registers, really, one for like an index or a key and value relationship, if you will. So one for my keys, and those correspond to what monomials contribute to then the values that are present in my value register. So I have these two that I'm operating with, one which is known, right? I have all my keys in equal superposition, and then my value register, which is of course determined by the problem. And what we did is we performed that addition of the monomials, or the sum of the monomials, by composing rotations, which I think is a pretty common building block in quantum computing. And it's also nice in that it gives us a implicit understanding of the negative values and the coefficients. So that's one piece. I call that a state preparation operator. Then we need to know how to search for a candidate, which in quantum computing is Grover, of course. And when we're searching for the minimum, it's sufficient to just look for negatives, which if you're using composed rotations, what's convenient is that you get a sort of implicit 2's complement notation. So you get a sign bit, right, on the far left side.
Mm-hmm.
So you just have to match that one bit to find negatives. So that gets a really efficient oracle. And then the last piece that we need is you need some way, just like in any optimization problem turned into a search problem, to adapt and then narrow down that search space, which is sort of the adaptive part of Grover adaptive search. So I will say the definition for Grover adaptive search is here in the notebook if you want to read it. It's also available in the paper, which is linked here if you want to get a little bit more deep into how that works. But just to give a brief example, really what I'm constructing with this quadratic program to negative value oracle, if you go and look in the code, is that first piece, that state preparation operator, AY, which is going to make this state. And if you're not familiar with the math, really what this is doing is I want to take all the values of all the possible values of that polynomial, right, depending on the input, and I want to shift them by some threshold y, which is what this is. And we're going to start with 0, right? So we're just going to leave the polynomial as it is. And then throughout the course of this algorithm, I'm going to shift all the values up so that less and less values are negative. And then just by the definition of doing that shifting, at the end of this, what I'm going to find, if I can do it successfully, is that my minimum will be the only negative value left. So that's what this piece of the code is doing. If you go look there, the oracle is simply just looking at the sign bit, so very efficient. It's a match on one qubit. And once we have those pieces, we put together a fairly simple class to take the Aqua Grover, which takes a state preparation operator and an oracle, and try to find the minimum of the quadratic program class that Qiskit Aqua has put together in the newer, I think like a couple weeks back, there was a big Qiskit optimization push for Aqua, and they basically found a way to very quickly make nice polynomials like this, convert them into a program using some docsplex and things like that, and then plug them directly into a quantum algorithm, right? So I guess as far as a good example, I think a picture says 1,000 words. So really what's going on here in this example is I want to be able to map this input, right, my key register, to a value register. And we found a nice way to do that is with pixels. So if you're not familiar with complex numbers at all, you can actually map a complex number to the color wheel, which is what I'm doing down here. The intensity of each of these pixels is determined by the magnitude of the amplitude, and the phase is determined by the color. And I think there are a couple visualizations in Qiskit that do this now. I think the qubit one does it pretty well. And so, kind of like what I was saying, we start here with no threshold, and I just want to take like one shot just to see if I get it. Like I might get lucky, right? When I'm sampling with Grover. And so I'll just do that with no Grover rotations, which is what this R variable is. And I guess I kind of forgot to mention the reason of doing this is because in Grover adaptive search, I don't know how many rotations I need to find my value, right? So I need to figure that out adaptively, right? And that's part of reducing the search space. So there's 2 steps, really, adjusting that threshold and then adjusting the amount of times that I iterate with Grover. So here I'm just starting with a 0 shift, right? No rotations, just hoping I get lucky. I don't in this case, so we move forward to the next step. We rotate once, and in this case, we actually get all the positive values being the most intense, so we don't make any progress again. But 2 rotations is that sweet spot where I'm seeing all the negative values that are highlighted. And so I'm going to update my threshold with the value that I found, right? And so this is, again, where we're narrowing our search space. I'm going to shift up by 1, and you'll see all the values shift up here. So now that value that I just found becomes positive. And I'm going to keep doing that, right? That's basically what's happening through the rest of this document is as we go forward, I find better and better values until only one value is left, and one rotation of Grover search is going to get me my minimum. And of course, there's a lot of math and things, and in the paper we go very concrete into how this works and the optimality of this, or sort of the practicality of this. But I think it's kind of neat that in quantum computing I can just show you this image, and most people I think understand what's going on. And so I think that's really a great example of the kind of work that we're trying to do, is both to innovate but also educate. Yeah, I think that's it for the notebook.
So do the problems that you're studying, do they need to satisfy any condition, or is there any restriction for the quantum algorithm you just showed us and the circuits to implement the oracles that you use to be useful compared to classical methods?
Yeah, so I would say the initial algorithm addresses integers, and we address that in the appendix of the paper. But the method works for real numbers as well, and we have plans to update the algorithm in the future. But I think that goes back to the fundamentals, right? How do you encode integers, right? That's one thing. But then if you ask some people how to encode real numbers using rotations, they kind of shake their head. So how do we do that in an efficient way? How do we represent that? That's kind of the next step. And then not really, I wouldn't call it a restriction, but in anything where you're doing shifting like this and you have a set upper and lower bound, you have to worry about space constraints. So you kind of need to know, at least intuitively, what your search space looks like. And then as far as oracles, yeah, I would say the main cost that we look at there is, how many times are you calling the oracle? I think that's pretty common, but we also look at CNOTs, just because those are the main contributor of error on real hardware. And we looked at some Boolean logic representations versus what I kind of call signal encoding in this case, and we found that the signal encoding was more efficient. And that's not to say that other implementations can be better. I know there are some that might perform better under scrutiny, but we're always looking to improve.
So we have a question here. How near do you think you are to something practical where you will actually use a quantum computer over a supercomputer?
Ooh, that's a rough question. It's a common question, but it's the simplest questions are the roughest ones. I would say we're really not in that stage yet. I prefer to collaborate right now, and I think when we start to get to that stage where we're starting to run things on quantum computers for real, real business purposes, that's where we're going to transition to compete. And I think that's a years off. I don't think that we're going to be in that stage, even just from a practical perspective. If I need something to run in business, typically I need it to run now. And so how does that work with computers that I don't own, and so on and so forth. So a lot of people I think will answer this question with the technical ramifications. There's a lot of business stuff that needs to get solved before we even think about doing that, and that in itself will take a considerable amount of time.
Right. So in your problem, you can map to search space to integers. Is that all you need, and you'll be okay?
To map, if I can map,
if you can map to integers.
Yeah, I mean,
I think it's a question.
You can use that algorithm to find the minimum. But again, with all the restrictions and things that we just talked about, the space constraints, and presumably you would have to find an efficient way to encode your problem as integers, and that's another big consideration.
Right. I guess another related question that people might be wondering also is what use cases in finance in this case may benefit from this Grover adaptive search using your implementation of the oracles.
So in the paper, we gave portfolio optimization as an example. So we talked about how to convert a portfolio optimization problem to a QUBO, or a quadratic unconstrained binary optimization problem. And so that's what we addressed there. But I would say in general, that works for if you can convert it to a binary polynomial, and if you need to add constraints, as far as we've looked, or I should say to the best of my knowledge, this will work for any such problem.
All right, so people in finance, they use several methods to model different aspects of price, behavior of assets over time, or like risk, whatever important things you have for financial services in general or asset management in general. So maybe you can like share some thoughts on if and how one could leverage that knowledge and transition to quantum circuit models, or maybe use them in concert with quantum.
Yeah, so I would say in the same way that a lot of those approaches you mentioned tie into classical machine learning, and maybe even in those particular cases, I think quantum computing could play an important role in that field. And that kind of comes back to we want to apply quantum computing to all of those things if we can, but the answer to that question of will it be practical or will it be useful is still sort of an unknown. So I guess it's kind of a good point for leaving you, in that I would stress the fundamentals rather than jumping straight to those business problems, because the former will lead to the latter, right? So asking questions like for machine learning, right? The inner product is a very powerful operator. How do you do that efficiently in quantum computing? How do you efficiently encode, your classical data, right? Like converting that problem to integers. And if you can work on developing those good good building blocks, I think that those will lead to you solving complex financial problems, I guess, in the case of this example.
So I don't know if you can answer this question, or maybe you can give us like your experience, right? Yeah. But the question is, when did JP Morgan start getting into quantum computing, and what was the #1 driving force at the time to make you interested in starting in quantum?
I can tell you what is publicly available online, and that we started our academic partnership with IBM in 2018, and then again with Flare, being led by Marco, as of this January. So that's kind of like a general timeline, if you will, for people who want to Google things. What was the contributing factor? I would say, I think in general we want to be on the cutting edge, right? And typically, if you want to ride the cutting edge, you have to be a little bit ahead of when a practical use case is going to arrive. The last thing you want to do is kind of camp out and let things go on in the background and then try to jump on, because then you're already behind. And if we want to be the one of the best financial institutions in the globe, we've got to ride that cutting edge on basically every field that touches us.
Right. So with that, Austin, thank you so much for sharing all that with us today. Thank you for your time. I hope you enjoyed it. Do you have any final remarks that you would like to make?
I would say no, just thanks for having me. This was a blast. I will say, if this is your first circuit session, go watch the rest. These are great. There's another one with Zyra where they talk about other stuff in industry, and I'll leave you there.
Right. Thank you so much, Austin.
All right, thank you. See you later.
See you. And so now I'm very pleased and happy to introduce Eun-Sung Lee and Tanvi Gujarati to talk about how Daimler is exploring quantum. Right? Eun-Sung is a computational material scientist, and he's principal scientist at Daimler, more specifically Mercedes-Benz Research and Development North America. He graduated with a PhD in mechanical engineering with a minor in physics from Stanford, and he focused on energy technologies. His research interests include investigating new and advanced battery technologies and modeling battery performance. And more recently, he's also been working on quantum computing research, developing quantum algorithms for chemical simulation and machine learning, and studying use cases for industrial applications, including how quantum can be applied to data-driven material modeling, materials informatics, where he's seeking to apply machine learning techniques to materials data for the prediction of properties. But you'll learn a lot more about all this from him. He's joined by Tanvi. She has a PhD in physics from the University of Michigan, where she developed her expertise in quantum optics and quantum communications. She then joined us at IBM Quantum, working to discover and develop applications of quantum computing, and working very closely with industry to do that, as the industry informs, which are the problems that are valuable to investigate if quantum can offer an advantage and have benefits that we can see in our daily lives. But I will let them tell us themselves more about their backgrounds, their current research, and how they discovered quantum computing and got started. So, Yunso.
Thank you, Zaira, for kind introduction. So let me talk about myself. Okay, so I got a PhD from PhD in mechanical engineering and minor in physics from Stanford University, and then worked as a postdoc, chemistry postdoc in Berkeley National Lab. And then I moved to Alabama to work as an assistant professor in the University of Alabama in Huntsville. And then I came back to the Bay Area to join the Mercedes. Yeah, that's my journey and how I got in this field. My research background has been in the computational material science. So I just developed a new method and applied the developed method to solve the more practical problems. So everything related to the computational method always has been a very strong interest to me. So when I was offered the opportunity to work on the cutting edge quantum computing research, yeah, to me, it is so hard to decline that, right? So in the company, I have two roles. One is for the quantum computing research, and the other one is advising to the battery research and development for Daimler. But today's session is only dedicated for the quantum research, so I'm just share my experience for experience with the quantum computing research. And let me see. So even for the quantum computing research, my research interest has a very various topics, right? So because there is a very wide spectrum of potential quantum computing applications for automotive industries, and my research interest is also aligned with that. So for example, we can calculate the material properties using the very accurate quantum chemical simulations, while we can also develop the quantum machine learning algorithm and combine that algorithm with quantum chemical simulations. And then the impact will be huge to accelerate the development of new materials. Actually, that field is called the materials informatics, and I'm going to talk about that later today.
How about you, Tanvi?
Thank you, Zaira, for the introduction, first of all, and hello, everyone. So as Zaira mentioned, I work as a quantum computing applications researcher with the IBM quantum team. And it was not many years ago, I was a PhD student at the University of Michigan working on problems which were more related to quantum optics and quantum communication. And around that time, I kind of heard this exciting discussion, amongst my friends where they just described how they had started, running a few quantum circuits on the IBM quantum experience backend at that time, the 5-qubit devices. And that kind of got me started to think about these problems. Fast forward a few years, and now I'm glad to be working in the field of quantum computing problems, to develop good algorithms. And this area has been developing so much in recent times. So in my day-to-day, what I try to do as my job is find some unique avenues and research opportunities where one can get some interesting applications for different quantum computing algorithms. So to that end, I get to kind of work with very, talented and experienced researchers from many, many different fields, like Insecure, and develop some interesting applications for quantum computing. Yeah. So yeah, that's my quick introduction.
Thank you both. So can you tell us, for both of you, can you tell us how you see quantum circuits and what they mean to you, given the work that you do?
Maybe Insecure, you go first. Yeah.
Okay. Yeah. So if you ask that questions a few years back, then probably I would say that the circuit is just electronic circuit to me. It's just a PCB board with the capacitors and then some of the microchips, right? And I think that'll be kind of a common response from the general engineers who have a background in engineering, but are not part of a quantum computing society. And I can see the similar things happening when I try to talk with my friends and colleagues about the quantum computing, because when I explain the quantum computers, what quantum computers can do and what will be the essential part of the quantum computers and what quantum circuit is, and then they started to think that there's some circuit inside of a quantum computers, something like a FPGA, so we can just programming using that circuit. And then I say, oh, that's not right. That's not true. Quantum circuit is more like a virtual circuit, right? And then they started to get lost, right? And to me, another story is that to me the quantum computing looks quite similar to playing the pinball game. When you play the pinball game, you shoot the ball, right? And then that ball just bounces back and forth between the spinners and bumpers and finally drops, right? So there is some similarity between the quantum computing and the pinball game. The playground of the pinball game should be something similar to like the quantum circuit, right? And the bumpers, spinners, they should be something like unitary operators, right? So yeah, just imagine there is some quantum version of a pinball game, right? So that the ball is now the quantum state. Right? Isn't it interesting?
Yeah,
I
that's
love
a
that
very,
analogy.
yeah, I love it too. Like actually, we should think about making a quantum version of pinball game. It would be very popular.
Yeah.
I guess, I mean, I imagine something, along those lines too, and thinking about quantum circuits, like a sequence of gates and operations that can transport you essentially from one point in the Hilbert space to another point, but in a controlled way. Like you essentially can decide which state you are transitioning to next. So almost like traveling from point A to point B in this space described by the Hilbert space, where actually there are many, many different options of going, or different routes or modes of going to the from one point to the other point that can be carried out by different sets of gates or sequences in which you apply these quantum gates. Now, as a developer, I guess it is also an important question to ask: how efficiently can you do this process of taking a state A from state B? And that would be an important aspect to consider. For example, one must always pay attention to what are the different limitations of coherence times that are available for the different qubits, or different kind of errors which may not be just related to 1-qubit gate or a 2-qubit gate, for example. And also the connectivities over which you would like to implement your quantum circuit. So different physical systems will have different connectivities and different sets of basis gates that are more native to those devices. And I think all these questions need to be answered and kept in mind when actually creating quantum circuits for particular applications as a developer.
So we have some great analogies here. We have a quantum pinball game and we have a Hilbert space transportation system. So just out of curiosity, do those include classical computations, whether they are concurrent or non-concurrent, or do you only include unitaries plus measurement and reset?
So in that the quantum version pinball game, there is just the shoot the ball and then we watch it just until it drops, right? So there is no classical part in there. Yeah. So it's just a purely 100% quantum version. But it depends on your interest. If you are interested in using the result of your pinball game for something else, then probably you can develop some classical algorithms and combine it with the result of your quantum pinball game, right? To use for that application. So yeah, I think I forgot what the quantum circuit means to me, right? So I just talked about what is the circuits for the few years back of me, right? So for now, though, I can say that the quantum circuit is a quantum circuit to me, right? And then the quantum circuit is just a collection of all the mathematical operators. They can adjust the quantum state in a way that I want, right? So that I can run the quantum algorithms on the quantum computers.
Yeah, essentially, when I was thinking about this analogy of transporting between points A and B in the Hilbert space, I actually was just focusing on unitaries and measurement operators and resets and things like that. But thinking about it, like a Hilbert space is a larger space compared to Euclidean space. So maybe we could still, like push that analogy further and think about, how you could have some classical operators embedded within a few sets of, few implementations of these states where you have some transportations happening in the Euclidean space and then push them back again into the Hilbert space. I don't know. Maybe that's a way of looking at concurrent classical and quantum computations. Well, I guess
that would put you there in a mix between like a purist and a rebel in the spectrum, right?
I guess so. Yes, I guess so. I think, yeah, but that analogy needs to be polished quite a bit.
Yeah, of course.
You have some work to do. All right,
Yeah.
so let's
Right.
explore this a little bit more in the context of your research. What kinds of circuits have you been using or investigating as you work to develop applications for the auto industry?
Oh, yes. So now it's time to talk about our research. All right. So yeah, I've tried and I have used several different quantum algorithms, of course, because there's a very wide spectrum of potential quantum application for automotive industries. But as I mentioned earlier, today I would like to just focus on the materials informatics because there is one of my primary interests today. And yeah, the materials informatics, again, there is a field of a study that combines the computational material science and data science techniques. So what we usually do is that we collect the data from the result of computational material science. Usually that is just quantum chemical simulations, right? So we collect the data from the quantum chemical simulations and build one big database. And once you have a big database, then we can use it for several different applications. For example, you can use that database to pre-screen the materials, or you can just use it to predict and design the totally new materials so that we can accelerate the development process and deployment of the new materials. And this field is very active and still growing. And recently there are many newer methods combining the machine learning algorithms and neural networks to analyze the materials properties and behaviors based on the data from the quantum chemical simulations. So this should be, I think that this is a very interesting topic for just general material scientists. Okay, and that's why and for the success of the materials informatics, there should be the two important factors that need to be addressed. At first, we should be able to get very accurate data. That means that the precise result from the quantum chemical simulation. And the second factor is that we should be able to deal with very large size data efficiently. And that's why recently we started explore the application of quantum computing, more specifically the use of a quantum circuit to model the quantum mechanical interactions or interactions in the crystalline materials. So basically, this is still under the theme of materials informatics. So we adopted the learning-based approach. So we designed the parameterized quantum circuit and train it by supervised learning using the data from the quantum chemical simulations. So let me put up some slide and then talk about a little bit more detail. Let me see. Okay. Can you see my slide here?
Yeah, I can see it. Yes.
Okay. So this slide shows the overall workflow of our algorithm. So basically it consists of a quantum classical routine here and the anomaly detection and treatment part here. And quantum classical routine is a kind of a smaller loop. So in this small loop, we start the training based on the data from the training set. Right? So here the sigma is a kind of an index to specify which atomic species are residing on the lattice site of the materials. And E is the energy. There is a coefficient of a quantum circuit and at the initial step, these values will just randomly selected. And S is a scaling factor to adjust the overall scale of the energy. Right? And inside of this small loop, at every step, we calculate the energy of the material as a function of a sigma using the quantum circuit, which I'm going to describe in the next slide. And then after the EQC is calculated, and we adjust the theta and S using some classical algorithms. Here we use the Covilla and Adams. So we try to, so we optimize the theta and S to minimize the cost, which is defined as a root mean square between the energy from the quantum circuit and energy from the data set, energy from the training data set, right? And after this small loop finished, then we check the performance of the optimized quantum circuit. And if it fails to meet the criteria, then we update the training set by applying the anomaly detection and treatment process. So here, let me point out this. We have used dense functional theory calculations, the DFT calculations, for the quantum chemical simulation method. And DFT calculation is, I think, is one of the widely used the quantum chemical simulation method, and is relatively cost effective, but it still has some risk of a numerical artifact and some unconverged results, especially when you use a DFT calculation for some materials containing some magnetic the moment. Okay? So this, including the anomaly detection and treatment process was very critical in our algorithm. And this slide shows how we calculate the energy using the quantum circuit. Okay, so we try to prepare the quantum state psi as a function of a sigma. Again, the sigma is indexed to indicate the atomic species on each lattice site of materials, and theta are this coefficient of a quantum circuit. And we prepare this quantum state by applying all these unitary operators on the initial state 0. Okay, and yeah, and then the detailed information about this U unitary operator is given here, and all these process can be described by this quantum circuit. Okay, so we start from the zero state as an initial state, right? And then this initial state pass through the series of Hadamard gate and layer 1, and another series of Hadamard gate and layer 2, and then measured with respect of XY the basis. And each layer, so we have 2 layers, and then these 2 layers have an identical structure, and each layer has these the RZ operators and entangling blocks and RX operators. And the main point in our the approach to build the tangible layer is that we assign the entangling blocks between the 2 nearest neighbor qubits. Okay? And then once we prepare this quantum state, then we calculated the energy as the expectation value of a quantum state psi with respect to the measurement basis. Okay? So, and then once we developed this algorithm, then we apply this algorithm for the A-lattice site LCO system, the lithium cobaltate system. And then these are just the results. And in the left figure, you can see that the energy predicted from the quantum circuit and energy obtained from the DFT calculations. And then you can see that these two agree quite well, right? And then the cost in terms of the root mean square error between the EQC and eDFT also keep decreasing as the algorithm proceeds. And once we obtain this optimized result for the quantum circuit, we use it to predict the energy of unknown sigmas. So this is just a testing. This is just a demonstrating of a feasibility using the testing set. Okay. So these are just a result. Left figure, right figure shows the comparison between the energy from quantum circuit, energy from the DFT calculations before anomaly detection and treatment process is applied, and after the process is applied. Okay, and then you can see that from the left figure, you can see that even without the anomaly detection treatment, the energy from quantum circuit, energy from DFT, they agree quite okay, but there are still some of the outliers, right? But from the right figure, you can see that all those the outliers can be just gone, right? After we apply the anomaly detection and treatment process. So I think this is a very good evidence to show that our algorithm actually worked quite okay, especially when it was combined with the anomaly detection and treatment process. And the final result is that the cost in terms of RMSE just 0.045 electron volt cation. And the MAE, the mean absolute error was a 0.037 electron volt per cation. And I think this is a quite okay accuracy, and the accuracy can be quite acceptable, especially when you consider the overall scales of this energy. I think, yeah, that's all I have. And Tanvi, do you have something to add?
Yeah. I also want to add like just a few comments on the kind of circuits that can be used. So in general, like there are different, there's a plethora of different circuit models that one can use or explore for these material science kind of data sets, right? One key consideration is to pick circuit models which are like very hard to simulate classically, and see if there's any advantage in using such circuit models, because then it's like using a completely different or a new novel class of models to learn the data sets from material sciences, right? Also, as I was mentioning earlier, when designing these circuits, it's important to take into consideration what kind of devices do you want to run them on. So, for example, the connectivity that we chose in our circuit was linear connectivity, based on the fact that we have linear connectivities available for the devices that we would like to run these on. There are many such considerations that one can take, for example, which basis set gates to use and things like that. So it
So
remains like...
Now that you're talking about the considerations and how you choose things, we have a question about like, why do you add a layer of Hadamard in addition to the single qubit rotations in each layer? So I'll make that a little bit more general. Like, what is the intuition for the choice of gates and the sequences of gates that you use in the circuit?
So initially we tried using gates that were only based on Z rotations, but our data set has essentially a plus or a -1 as input states, which kind of is constrained by the parity, because there can be many such configurations which would have the same parity. And if we were using a fixed set of measurement operators with only diagonal gates, then we were seeing that many of the same configurations ended up giving similar energies. To therefore distinguish between different such configurations, we introduced some additional rotations that would change the diagonal nature of the circuit, essentially. And so do you want to add something to that?
I totally agree with your point. Yeah, that's why we adopted the data specific the rotating operators. But again, there can be the many other variant in terms of your choice of the operators. We just try to make our quantum state and quantum information dispersed in the much larger space, so that the parity issues that can be just mentioned can be just minimized.
So Tanvi, you also mentioned an interesting question about like how to look at what materials can be best modeled by which methods, right? And so a lot of people may be most familiar with VQE, perhaps the most popular method that it's used to estimate energies of states in quantum chemistry problems that using quantum current and near-term quantum hardware. So can any of you compare your algorithm to it in terms of like when would you recommend one over the other, and how do you expect the performance of both to compare?
So I guess like
Yeah,
one of the... Do you want to go ahead and say?
it doesn't matter.
Okay, so let me just mention that the goal of VQE essentially is where you are trying to find the energy of a particular system, where you know what is the Hamiltonian of that system, and you are trying to find the eigenvalues of that particular system, right? And the hope is that even VQE being a heuristic algorithm, that you would eventually get to the ground state or the state that you're interested in. With using this particular approach, we are trying to answer a different question, which is essentially, let's say that I have data set for some quantum chemistry calculations that were already done, but these are very expensive calculations. Then can I use a quantum circuit model to learn the properties of these data sets and predict energies for some configurations that I don't want to calculate the energies for, because it's an expensive calculation to have. So let's say that I have a X number of data points, and I want to explore what would happen when there's larger set of data points. then I can just use this learned model and extrapolate from that essentially. So in that sense, I think both the algorithms have a different flavor.
Yeah, that's a good point. So yeah, just a practical point of view, I recommend to use a VQ just to calculate the energy over one specific molecular conformations. But if you are interested in to predict the energy over entire all possible conformation of materials, but with a little bit of a compromise in the accuracy, then definitely I recommend to explore, study, and use our algorithm.
So what's the advantage of using a quantum circuit over a classical machine learning algorithms in the case that you're interested in this case in particular for the auto industry?
So do you want to answer that question?
Yes. So definitely we claim that there are the computational advantage in our algorithm. At first, the number of explicit parameters is linear in our algorithm. So just imagine that you have some materials that you would like to model, and you don't have any pre-knowledge of the materials. So you don't know any domain knowledge, how longer the effective range of the interaction between the two atoms, and you don't know what will be the symmetry inside of the materials. If you have those pre-knowledge, then probably you can just use some kind of a very classical approach in polynomial numbers of operations. But without those pre-knowledge or domain knowledge, there's no way to avoid using the the exponential scaling numbers of the parameters. But if you use our algorithm, the number of parameters is still the linear. It's scaling linearly in the number of the lattice sites of the material. So I think there is definitely some computational advantages there. And then another advantage is that if you use our algorithm, we don't need to cut down the feature space. We just combined all the features. We start from the very small input space, but inside the quantum circuit, that input space just combined to each other, right, to create a much larger feature space. So you don't need to cut down you don't need to truncate your feature space, so that when you actually do the anomaly detection, it is very important to possible as many information as possible. You need to include as many information as possible inside of your training set, in your feature space. So in terms of that, I think we believe that our algorithm has definitely have some strong advantage compared to the classical algorithms.
Just to add to what Unsuk mentioned also, the fact that we are modeling systems that have intrinsically quantum mechanical interactions. So maybe like a good way of understanding these interactions might be to use essentially quantum circuit models rather than normal normal machine learning models, for example, to learn the intrinsic properties of these data. And maybe that would provide an advantage when trying to understand these properties.
Okay. All right. So, well, I mean, thank you, Eunson. Thank you, Tanvi. It's been a pleasure to have you here today and learn from you. Do you have any final remarks?
Thank you, Jaira. It was really my pleasure to join this session and to share my experience with you guys. And thank you for inviting me.
Yeah, I want to say the same. Thank you for inviting us, for hosting us, and giving us an opportunity to discuss this work. And thank you, everybody, for listening as well.
Yeah, it was a pleasure. And thanks to everyone that tuned in. Thank you for joining us in the discussion. We love your participation. And we hope to see you next Wednesday, same time, noon Eastern time, where we will be talking about how to benchmark quantum circuits. So please don't forget to subscribe and enjoy the rest of your week. And I just want to thank again you, Eunson, Tanvi. Thank you, Austin, so much. And see you all guys next week.
Thank you.
Yeah, thank you. Bye-bye.
Bye-bye.